In a South London sixth form college, something strange and shiny has got people puzzling.
What's it made of?
Rubber. Foil.
Probably solid steel.
It's made from foil wrappers from chocolate bars.
Really?
Rolled up, yes. Surprise you?
Yeah, that does actually.
She's not the only one. Bounce around the net for a while and you'll find a whole web of foil ball fans. For these people, Marcus Morris and Mike Pollard are heroes.
All started in 1993.
Yes, a colleague of ours called John Gilhooly used to eat chocolate bars like they were going out of fashion, and he used to leave the foil lying around, and we used to crumple up the foil to make office space, and after a while we thought, we're getting quite a ball of foil here, we might as well carry on.
Lunchtimes soon rolled into legend. Newspapers wrote stories about the Croydon ball. Marcus began to wonder, what if the ball kept on growing? Just how big could this thing get? In fact, there's so much aluminium in the earth. If you could somehow extract all of it in one go, you'd end up with a ball as big as the moon. There's so much aluminium, and it's so useful, that you could almost say we live in an aluminium age. This is how much a family gets through every year. From drink cans to saucepans, our homes wouldn't be the same without it. Here's why engineers get so excited about aluminium. Go on, take a chunk. It's not cheap, but it is strong and not that heavy. You can get the same strength in steel for less money, but it's much heavier. More strength for less weight than steel. That's what makes aluminium the secret ingredient that lets the world fly. Robert Grimwood flies ultra-lightweight planes called microlights. At 19, he's Britain's youngest microlight instructor.
The most important metal in the aircraft is aluminium. We're looking for a very light metal which is also very strong, and aluminium obviously fills that role very well.
So well that people have flown microlights right around the world.
There is a considerable amount of aluminium on the aeroplane. The whole of the wing structure is all made from aluminium poles. Then the control frame here is all aluminium. The front strut is aluminium. The main monopole is all aluminium. The undercarriage leg here is aluminium, and all the engine block and the carburettors and gearbox.
This workshop makes spare parts for Robert. Aluminium is quite an easy metal to work. You can bend it. Aluminium is malleable. It's easy to press or roll thin sheets. And you can stretch it, up to a point. When a pilot's life hangs on a piece of metal, it's vital to know it won't break. So this machine pulls test samples until they snap. This sample isn't pure aluminium. It's a mixture with other metals called an alloy. The alloy is stronger than pure aluminium would be, but it still stretches because it's quite ductile. It draws out when you pull it. Every time you rip open a ring pull, you stretch and break aluminium. It's so ductile and malleable that the bottom of a drinks can is all one piece of metal, pressed out of a flat sheet when it was made. In thousands of ways, the physical properties of aluminium let us all fly. But there are more secrets locked up in its chemistry. Once the Croydon Ball got its own website, its fame grew and grew. All around the world, people started rolling other balls to challenge it. Marcus started getting email from people saying that theirs were bigger.
Our aim is to beat their aluminium balls in terms of size, weight, density, roundness, and of course using the one kind of wrapper that we started with.
Some people decorate their balls with Easter egg wrappers, but Marcus and Mike keep theirs shiny. That's easy, thanks to aluminium's chemistry. Aluminium has an invisible protective coating. To see how it works, you have to look very closely. The shiny surface of aluminium isn't quite what it seems. It's not pure metal. The outermost surface is actually a coat of aluminium oxide. It's a layer just a few atoms thick, so thin that you can see the shiny metal underneath. Whenever a bit of the oxide layer gets scratched off, it reforms very quickly, and that stops the aluminium reacting further. This is why aluminium foil is so good for wrapping food. The oxide layer stops the aluminium reacting with the chemicals in the food. But take the oxide layer away with a kind of chemical polish like this, and kitchen foil comes to life. This is what happens when naked aluminium meets oxygen in the air. The reaction makes so much heat that steam forms near the surface. Still, shiny aluminium is secretly rather reactive once its oxide layer has gone. And if you grind it up very finely, it will even burn. It almost explodes. Heat from the Bunsen burner makes the aluminium react with oxygen in the air, and a spectacular chain reaction begins. The white smoke that's left behind is aluminium oxide. The trick, if you want to extract aluminium from nature, is to run this reaction backwards. And that's not such an easy stunt to stage. As the Croydon Ball grew, Marcus was getting more and more email.
We get a lot of fan mail from all over the world. We also get some hate mail.
The messages that really hurt were the ones that suggested the Croydon Ball wasn't made from foil wrappers all the way through, that it was a fake. How could Marcus prove they were wrong? What he needed was a solid aluminium ball exactly the same size as his foil ball. Then, if he could somehow get them X-rayed side by side, the world could see that the two balls looked the same. That would prove the foil ball was solid all the way to the core. It was time for the Croydon Ball to go looking for a twin, to go back to its roots in Australia. Most aluminium starts off in places like this. In the north, it's so remote that the last time a camera crew visited was 1976.
Bauxite, the ore of aluminium, one of the most useful elements.
They don't do that anymore, and they probably play different music. But the chemistry stays the same. Bauxite contains aluminium oxide, the raw material for aluminium production. The first thing they have to do is get rid of the impurities which give it that red colour.
The bauxite disappears into a bewildering array of pipes and vessels. Nothing will be seen of it for several days. After 4 days, it emerges, transformed into swirling crystals of aluminium oxide.
But it still needs to be dried.
At 1200 degrees Celsius, all chemically combined water is driven off, leaving a dry white powder, alumina.
Alumina is pure aluminium oxide. They ship it around the world to places like this, Anglesey Aluminium in North Wales. The alumina is kept dry in this vast building. Every year they get through enough to fill a football stadium. Getting shiny metal aluminium out of alumina is difficult and dangerous in the laboratory. So it's easiest to see what's going on first in a demonstration using another white powder. This is lead bromide, and the 2 black rods are electrodes made from carbon. They're connected to a power pack. The circuit also includes a light bulb. As soon as a current flows, it will glow, but for now it's dark because lead bromide doesn't conduct electricity at room temperature. Alumina is the same, but heat it up, melt it, and everything changes. Now a current starts to flow. Bromine bubbles off at the positive electrode, and near the negative electrode, molten metal sinks to the bottom. Extracting aluminium from alumina is very similar. It just needs a lot more heat and a lot more electricity. Every day, this plant makes enough aluminium for a foil ball the size of a house. There's over 5 tons of liquid aluminium in this crucible alone. People say that after you work here for a while, you start dreaming about swimming in it. Claire Archer is a chemist. She runs the production process.
I've been at Anglesey for the last 5 years. First 4 years I was in the laboratory where I studied for a HNC. Then moved to Potlines as a process control specialist where I've been for the last year.
The pot line is the heart of the production process. It's a row of electrolytic cells. They call them pots for short. Inside, they keep alumina hot and molten with massive electric currents.
Currently the pot lines are running at 163,000 amps. In a day we use enough electricity to power a small town.
All that electricity does 2 jobs. First, the electric current heats the aluminium oxide. Heating breaks the strong bonds between aluminium and oxygen. That leaves positive aluminium ions and negative oxygen ions floating in the mix. Next, electric charge draws the ions apart and neutralizes them, turning them into aluminium metal and oxygen gas. Here's where the charge comes from: carbon electrodes. 16 cathodes line the bottom of each cell. Up above them hang the anodes, positive electrodes. It's a big job to replace them, but it has to be done often because the anodes get burnt up when the cell's working. Here's what happens. The massive electric current passes between the anodes and the cathodes through molten alumina. The current keeps it hot. To save electricity, they also add a material called cryolite. It brings the melting temperature down from 2000 to 950 Celsius. Alumina is made from positive aluminium ions and negative oxygen ions. When aluminum melts, the ions are free to move. They're no longer stuck together and can go their separate ways. Opposites attract, so the positive aluminium ions get pulled down towards the negative cathode. They pull electrons off the cathode, neutralising their electric charge. That makes them aluminium atoms, not ions, so they collect on the bottom of the cell as aluminium metal. Meanwhile, the negative oxygen ions get pulled up towards the positive anodes. There, they neutralise their charge and turn into oxygen gas, but not for long. The oxygen reacts immediately with the hot carbon anode to make carbon dioxide gas. Each one of these cells produces more than a ton of molten aluminium every day. They suck it out with a machine like a giant vacuum cleaner. They skim off impurities called dross. Then they make it into ingots. These ingots are like blocks of chocolate that get shipped out to customers. Customers then remelt the ingots to cast useful products. Here they're making a twin for the Croydon ball, starting with a mould made from sand. When it's ready, Marcus and Mike hope they'll get the X-ray they need to prove their foil ball isn't a fake. Molten metal goes in. What should come out is a solid ball, exactly the same size as the world-famous Croydon ball. It's a big day for foil ball fans everywhere. The solid ball cools, and it clearly needs some cleaning up. Question is, will the Croydon ball match it in an X-ray test? If it does, this trip should silence critics of the Croydon ball once and for all. At the Welding Institute, they can scan for anything unusual in metal objects. With her X-ray vision, Jan Walker has the power to find out if Marcus and Mike are hiding anything.
This is a solid ball, so we just have a black sphere in the middle. You can see a few light areas around the edge. That's really where there's not as much material there for the X-rays to have to pass through.
But what about the foil ball?
There you can see your ball. In the centre you can see the areas where it's not as compact, not as dense, and let more X-rays through. The dark line on the outside shows where the wrapper's been pushed on harder. So you've got a more solid layer there.
So I've been doing rather better since...
You've obviously pushed the wrappers on much harder there.
Well, that's the evidence I need for the website. The X-ray showed that density is rising, and I can prove that it's foil all the way through.
It's just what Marcus was looking for. The Croydon ball has met its match, and no one can ever bring a fake again.